All right, thank you very much. Can everybody hear me? I just wanted to thank Ed and everybody here at the Segal Institute for the invitation, the opportunity to talk. What I'm going to be doing is kind of giving you a behind the scenes. I spent the last 3 years writing this book, which was specifically geared towards teaching design students to be able to visualize. And the publisher wanted to call it Drawing for Product Design. So these are some spreads. They'll just kind of flip through quickly. I really wanted it to be called Design Visualization because I think sketching or even drawing has a very narrow scope to it. So in any case, I didn't win that battle, which is perfectly fine. They already had a series and this was intended to fit into it. But what I did do over the next 3 years was begin the process of putting together what I thought would be a cohesive book for teaching design students to think more holistically about the visualization process. So that's not just about sketching. It's not just about rendering. It's a whole continuum that's completely tied to every other aspect of the design process. Including, and perhaps most importantly, computer-aided design. Because a lot of times my students will come to me and say, well, why do I have to learn how to draw when I can go ahead and just build it in the computer? My standard response is, if you want to build it in the computer, you're going to be stuck beginning with sketches anyway. So let's think about ways of interconnecting those things. So this was the abstract proposed for this talk. And I realized I've just come from 3 weeks of traveling through Europe doing a whole series of lectures. And they've been rather long lectures, usually an hour and a half. And so what I wanted to do was just take some of these key ideas and boil them down. I realized in an hour I wasn't going to be able to get through all of this, but I'm going to try to touch on a lot of these things. So what I decided instead was to compress it and finally compress it to this. As I went through the final presentation this morning, I realized open source may be something that doesn't end up in this presentation given the time constraint, but if there is time, I will talk about it. So visualizing complexity, insinuation of the frame. I'm going to talk about that first. And this may strike you as odd because I'm not really going to talk about drawing or sketching per se, but I'm going to talk about visualization. One of the things in my research that I was able to do, or what became obvious to me, was that there's a disconnect. When we think about the visualization process, I like to think of it, as I said earlier, as a continuum. That would be sketching, it'd be computer modeling, it'd be physical modeling, it would be strategic thinking, it'd be diagramming, it'd be mapping. They're all sort of the same thing. And so I'm very interested in trying to create a dialogue around visualization as a large continuum as opposed to a series of siloed kinds of activities. What I find oftentimes is that the best, not the best, but specific students have specific skills and they think that's enough. And usually I say to them, okay, you're good with that, but you also need to learn this skill as well. So in the course of the research, I spent a lot of time trying to make sense of the long history of visualization, going back to the Italian Renaissance. But I've also been very interested in just technology in general. So when I think of sketching, I think of it as a technology. And I see it directly connected. What the Italians did back in the 1400s is directly connected, and I'll talk about that in greater detail, to what we're doing with Alias or SolidWorks or any of the software tools that we have. So visualization has a rather complex history. And I like to point out that photography, which was really initiated in 1839, began as a workaround. To sketching. So this is William Henry Fox Talbot's sketch of Lake Como using a camera lucida. He'd used a camera obscura before that, but he's very frustrated. He didn't like the look and feel of the sketch, and he was using a tool to assist him. So basically, he's using a box with a lens to help him trace nature. It occurred to him that, in fact, he didn't need to do that, that he could use light and chemistry. So this is one of the first photographs that he created. But what I found it interesting that he's really started off his process of exploration into photography wanting to sketch. And so the book that he wrote, interestingly enough, was called The Pencil of Nature. But perhaps even more interesting is that he saw photography as something very different to, say, what we think of it as today. And I'll just pull this little quote. From the specimen given here, it's sufficiently manifest that the whole cabinet of a virtuoso and collector of old china might be depicted on paper in little more time than it would take him to write inventory, describing it in the usual way. So suddenly a camera could be used to take almost like a Cold War era photographer using a spy camera to record a document so that you can take this document back to your own authorities. So this idea that photography as a medium is not necessarily about capturing pictures, it's about capturing information. And so the idea of the frame becomes an immediate issue because at the end of the day there is an aspect ratio to the camera that constrains it. If we fast forward to someone like Cartier-Bresson, with his use of the camera all throughout the 20th century, what was referred to as the decisive moment, he's using the camera as a way to capture a split second in this continuum of time. And so we're looking at this image in a very different kind of way. We're looking at it as a fraction of a second, as opposed to something like an inventory. Or he's using the camera to move our vision from one person to the other and thereby connect them. So this goes back to, of course, older art traditions of composition, how we get people to read images. All of these things will become very important in design. So even using traditional things like diagonals to draw the viewer's eye through the image, while he's using this as a way of creating a fine art photograph, there's also a kind of technology there. There's a visual technology, there's a compositional technology. Same thing here with this wonderful photograph of a cyclist and this kind of, this almost helical staircase. Or using a camera to capture a very specific political event. And again, the sort of connections that occur compositionally that we forget to look at this as a fine art image because it's really not a fine art image. It's an image about a specific moment in political time, in this case in Paris during the Nazi era. So this was Cartier-Bresson's toolkit, a Leica. The artist Saul Steinberg created this homage to Cartier-Bresson. And I put this up here because I think it's quite interesting. If you look at the lens of the camera, what he's replaced it with is a connector that would typically be associated with a hose. So for Saul Steinberg, he's saying that Cartier-Bresson's camera is this collector of just a massive amount of data. All the data is just flowing literally into the camera. This is a more contemporary Haitian little folk art of a camera. And I think what's interesting here is that the presence of the individual caught is actually inside the camera already. They're not coming into the camera, they're in fact already in the camera, and the camera is sort of releasing them. So we have this very curious connection to technology that we don't always necessarily think about. But I like to feel that as a designer, I do my utmost to hack technology, to figure out what I can do with it. And I think one of the people who was perhaps most successful in that worked for this man, Leland Stanford. So this is a photograph of Stanford from the 1870s. When he had his official portrait done, it was actually done in paint. So even at this time period, it was more prestigious to have somebody paint you while you sat for the portrait artist. And so this is Palo Alto, ground zero for the digital revolution. And the digital revolution, in my mind, was kicked off by Edward Muybridge. Because Muybridge was solicited by Leland Stanford to settle a gentleman's bet about whether the hooves of a horse all four of the hooves of a horse were ever off the ground at one time. So Muybridge, being an eccentric landscape photographer, said, okay, I'll take on the challenge. And Stanford promised him his best engineers. And what he basically did was created a way of capturing this. And so in 1877, he proved that Occident's 4 feet were off the ground at any one time, and therefore settled Leland Stanford's bet. And the way that he did this was he took that technology, which was a series of cameras, and connected tripwires to them. And as the horse ran past that bank of cameras, it tripped off a sequence of images. Now, little did Muybridge know that he was creating a precursor to cinema. That if you took each one of those frames and you ran them sequentially, you would get what was essentially a movie. Of course, he didn't realize that. Stanford didn't realize that. But in the process of hacking photography, he creates this whole new medium. So if we were to take a Victorian optical toy like the zoetrope and add Muybridge's images in there, by spinning it and staring through this aperture, you're creating the necessary break that your brain needs in order to make each one of those images come together in a continuous stream. 33 years later, in 1910, in Frankfurt, Max Wertheimer, one of the founders of Gestalt, had come upon a similar kind of phenomenon that made him very curious. He saw the blinking of the railroad traffic signal, or crossing signal, and what he saw wasn't an on-off kind of discrete situation. He saw a jumping back and forth between those two states, which made him get off the train at Frankfurt and in turn buy a zoetrope, create some little drawings, and basically create a test tool, hacking photography essentially one more time, or cinematography, to also come to a better understanding of how the brain works. So again, there's the zoetrope. What Wertheimer did was he just created simple sketches, but the very same toy or optical toy from the Victorian era to make that work. So this is an image you can download from the internet, and you can see it's exactly as it was used by those early precursors. What the Gestaltists did was they were interested in the whole idea of pattern and shape recognition. So they realized that the brain is really this pattern detecting machine, and that there are probably some underlying laws that dictate how it is we see structure, how it is we see order. This is just a small sampling of those. But they continue to impact the way we see and understand design. So, you know, this idea that we live in a world that is defined by patterns, and that Henry Fox Talbot had already predicted so long ago that the camera was an ideal tool for actually recording this kind of taxonomic knowledge of stuff. If we now fast forward to industrial design in the late 20th or early 21st century to something like Thoughtless Acts by IDEO, we find photography being used in a very different way. The camera is being used ethnographically to record information to, again, detect patterns. And these patterns are patterns that then assist designers in developing user-centric solutions. And while some of this stuff may appear to have absolutely nothing to do with design, what in fact it's doing is capturing the sort of minutia, the little things that we don't always detect, and making a kind of catalog of it. So in Jane Fulton Surrey's description, she goes in and describes the way in which images like these can be used to begin thinking through very fundamental ways in which we interact with objects on a kind of everyday basis, leading once again to a kind of taxonomy. So for her, Thoughtless Acts was about adapting, exploiting, reacting, grabbing, warming, stroking. And the team had gone through multiple years, through multiple design programs of doing a lot of photographing and then putting those images up and reading those images and extracting from those images fundamental underlying sorts of motivations on the part of humans and how they interact with their products. This, of course, all results in, ideally, objects that have been designed for the user with a real sense of empathy for how people naturally interact with things, even if they're as complex as a medical device or as simple as just packaging. But this is what designers have done. We're using visualization tools, whether it's photography, sketching, diagramming, to understand end users and also develop solutions for problems. So cataloging something as simple or mundane as vanity plates can tell an interesting story, as this next slide demonstrates. The plates act as literal tags similar to the folksonomies that help organize social networking sites like Flickr. So these are my own images, and I oftentimes use photographs as a way to get my students to realize that there's a very interesting world out there if they just open their eyes and start noticing. And what I tend to find is patterns. And so I'm throwing up a lot of images very quickly, but I suddenly see that all these objects are talking to me. They're telling me curious stories. And so I've begun to organize my visual images around specific sets of taxonomies, very similar, like I said, to how you might tag images on Flickr. So in the end, you see professions, you see belief systems, you see a desire to make somebody laugh, you see a certain degree of bravado. You see people needing to communicate to the outside world what it is they do and how it is they do it. So images can be extremely powerful in communicating if, in fact, we open our eyes and actually see. So that's my favorite. I live in Heavenston. This is actually parked about 3 blocks from where I live. I've since seen that same plate, but spelled a slightly different way. Of course, the thing is, if you have an Illinois plate, you can spell it only one way, and then you have that name or that tag. So somebody was so in love with Heavenston that they found another way to spell it. But I couldn't find it when I was putting this slide deck together. If we could keep them for the end, because I've got a lot of material to get through. Sorry. All right. So just going back through those images, we learn what people do, what they believe, desire, value, stand for, wish for. Using visual tools, thinking about the world as a kind of decodable space and how we as designers make sense of it, I think is as essential as any other visualization process. This next slide is showing how diagrams can be used as a visualization tool, and this is actually from Herbst Lazar Bell, a program that they were involved in. I use this as a case study for the book. They've scrubbed all the client information from here, so it's a little generic. But in any case, what I'm really interested in is the way that designers and researchers start out. They have a lot of data, and they're trying to make sense of it, and they're trying to communicate. So initially, that's not very attractive or very communicative. They go through another iteration. They go through another iteration. It's starting to get a little cleaner, a little bit more direct. They go through another iteration. They're starting to use overlapping. They're not only in this Cartesian gridded space, but now they're also thinking about overlap. They're thinking about hierarchy. They're thinking about size. They're using all the things that we have available to us. And then finally, they start to push it out into something that's much more visual, three-dimensional. And then that in itself gets iterated in multiple ways until it finally arrives at this, which, again, using tools like Adobe Illustrator where you have transparencies or opacities, you can generate this kind of graphic pretty quickly. But ideally, it'll communicate across a broad array of people, from designers to engineers to managers to marketing people, in ways that keep everybody organized. So finally, there's the frame itself, which is what I started off with, this insinuation, the way in which the frame insinuates itself into what it is we do and how we do it. And I like to point out that comic and graphic novels have crept back into the design process in a big way. So if we look at the frames here, and we bring up Scott McCloud's Understanding Comics, you realize, and if anybody's unfamiliar with this book, it's a fantastic book. It explains how comics work through a comic. A very, very smart guy. But his use of space and size and hierarchy and framing devices to move your eye through that whole process. When I come to the section devoted to scenarios, I'll talk a lot more about how things like the graphic novel and comic books are impacting the way we put scenarios together. But what was interesting, again, is in this research, 1845, this artist, Rudolf Töpfer, was already creating a kind of comic book that merged text with image and had a keen understanding of what happens when you take the frame and you start to manipulate it, to the point where the frame becomes such a noticeable component, almost abstract, right there, that it tells a very, very different kind of story. So I think when a designer is up against the wall and they're trying to tell their story as visually as possible, they will take any of those pieces and they'll manipulate them as much as possible. All right, so the next section is use versus technology, mapping and form giving. One of the things that I was really interested in right from the beginning was to look for a metaphor. Since much of the book is really about drawing, I'm always looking for metaphors and analogies. And for me, maps became kind of the primary metaphor. It's a metaphor that spans strategy as well as actual design, sketching, and visualization. One of the things that I'm most amazed about is the human ability to sort of shrink yourself into that map space. So when you're staring at a plan view of a map, you're sort of shrinking yourself into that space and walking through it while you're looking at it. So there's this kind of macro-micro that happens. It's just because we've been mapping things for so long. So in the book, I used a lot of mapping metaphors, from basketball diagrams to Google Maps to clocks. And this became kind of a central, as I say, metaphor. Cartesian space became a central metaphor because it's what connects old Italian perspective sketching to computer-aided design. But it also connects data, how we map data in Cartesian space, and how we're able to, through simple technologies like Excel, generate spreadsheets, pie charts, etc. All of that is being occupied in sort of the same space, this very mapped out Cartesian space. So the map starts out with Ptolemy superimposing the grid over a spherical space so that the sphere can be flattened and we can measure distance from point A to point B. If we think about drawing and we take, this is a SolidWorks mountain range, what's happening in sketching is that you're simply taking a cross-section. I can't take an infinite number of slices off of this, and I don't need an infinite number of slices. What I need is a few slices from this and the intersections that result from those, and then all I do is I compress those into a flat space. Now if I add text, if I add color, say blue, you know that that means water, green, yellow for sand. I can take three-dimensional space and I can compress it onto a two-dimensional plane, but I'm essentially taking a kind of map and flattening it. I also like to think of sketching as a mapping activity. So this is Evanston. This is where we live. This is my map to the local Barnes & Noble. When I walk out the door, the last thing I do is think I'm going to go up to this street, take a right, go 2 more blocks, take another right. Google's going to map it for me, but if I'm familiar with the territory, I'm never thinking about how I'm going to get there. What I'm doing is saying, I know I generally need to be over here, and I'm just going to walk. Obviously, I live in a gridded city, so it's fairly easy. I'm not going to get lost. It'd be a bit more challenging if I was in London. But my point is that we should think of sketching as a journey. We shouldn't think of it as an end result, because if you think of it as an end result, you don't have the luxury of enjoying the process of getting there and not knowing where necessarily the direction you're taking, but ultimately the end goal you want to get to. So Kevin Lynch was an influential urban planner based at MIT. And I think one of his, for me, this was a real revelation. I was constantly looking for ways in which I could pull from different disciplines. So since he's an architect and urban planner, I was very interested in the way he was describing the human interaction with space. Basically, these five attributes: paths, edges, districts, nodes, and landmarks. What does that look like? Well, this would be a path. This would be an edge. This would be a region. This would be a node. And this would be a landmark. So if you're downtown Chicago, a landmark is going to be Sears Tower or the Hancock Building, something that's quite tall. If you're in Paris, it's going to be the Eiffel Tower. But we tend to have this kind of knowledge that, okay, this is the district where things happen. You know, maybe it would be Northwestern University as kind of a region where specific things are happening. But we have a very specific kind of relationship to maps in general. That comes partly from the way our brains are oriented. So we've got a parietal lobe, which is considered the where lobe, and we've got a temporal lobe, which is considered the what lobe. And so this idea of mapping goes back to Penfield Wilder, who was an American-born Canadian neuroscientist, neurobiologist. And what Wilder did was he actually cut the top of the head off of one of his patients. There are no pain sensors in there. You can actually pull it off. And he began probing with electrical probe into the brain to discover where in the brain are the various parts of the body mapped, because he was convinced that they are specifically located in discrete parts of the brain. And because the patient did not need to be anesthetized, the patient could say, they could say, that's my, I want to move my right arm. In some instances, he would probe and the arm would move involuntarily. In other places, he'd probe and the person would say, I have this desire to move my arm, because that's the premotor cortex, which is the desire, the part of your brain that's communicating what you're going to do, and then the actual brain itself, which is doing the physical motion. So from that process, he was able to map this somatosensory strip, defining that the hand, the size of the hand, the size of the lips, the size of the feet, all of these physical parts of the body are directly mapped very specifically on the brain, and they're represented much larger than other parts. So for example, your elbow does not show up in a large way on the map of your brain because you're not getting input from your elbow. But you're getting input from the tips of your fingers. You're obviously getting input, especially as an infant, from your lips and your mouth. And these things get literally mapped directly onto the brain. So here's a cleaned up version of it. And you see just how large the hand and certain aspects of the face are. And they've literally been mapped on there. This is a more contemporary version. And these are still all mapped as he had mapped it back in the 50s. I like, as a designer, to say to students that I don't have eyes in the tips of my fingers, but if I reach into my pocket, I can decipher whether it's this key or that key, or whether it's a quarter or a penny, just all through feel. So we've created these somatosensory maps that allow us to know I'm touching the right jump drive because I have 2 of them in my pocket, and I can pull them out without having to empty the contents of my bag. And so that's quite an amazing thing, and it's proof of just how directly critical the mapping that occurs at an early age between the physical body and the mental representation of it is. So for something like interaction design, we now are in this realm where we're designing smart products that have to communicate with us. But even if my wife is reaching into her bag for her smartphone, her iPhone in this case, all she needs to do is really touch one small piece of it, that fat radius that the Apple iPhone has. Or she can touch the back of it. She can know it's the phone. Or she can, in fact, feel with the tips of her finger either the hard, cold metal or the hard glass, and she immediately knows it's the object she's looking for. So we've mapped all those things very directly. Don Norman talks about this in Design of Everyday Things. One of my favorite chapters is Knowledge in the Head and in the World, because what he goes on to say is, again, getting back to sketching, information is in the world, great precision is not required, natural and cultural constraints are present. So going back to this idea of walking out of the house and navigating to Barnes & Noble, information is in the world. I don't need to know where I'm going necessarily. Great precision is not required. I have a general idea of where I want to go, and I don't need anything more than that. And then there are going to be natural constraints. Those might be in the form of corner stop signs. In this case, it'd be the grid. So trying to reconnect visualization in the design realm to how we actually think and experience the world, I think is an essential part of that process. So here's a Google map of London. And here is the same map where we've eliminated the satellite view and we've superimposed the traditional, very, very accurate map as we understand it. And then if we want to get around the underground, this is what we're going to be relying on. This is still a map. It's no longer proportionately accurate. These distances are not necessarily accurate. But the brain is able to superimpose this over that other map, and it can understand, I mean, here's the Thames. It's no longer nearly as serpentine as it was, but it's there. All the things are there, and we basically relearn the space, the underground space of the city, and we superimpose it on top of the physical space. And with things like Google Maps now, we're seeing the world in ways that we never did before. Obviously, when this historic map was created, we didn't know what the world looked like. We hadn't gone to the moon at that point. We hadn't done a lot of things. But the point is that this is a diagrammatic map. It's giving us a different kind of representation of the world. And I would argue that this is much more like a design map rather than a geographical map. I did a lecture at Central St. Martin's, and the designer sent me this map. I had on my iPhone Central St. Martin's all mapped out, but it was great. He gave me this. I converted it to a PDF and put it on my phone because he knew I was coming out of this tube stop, and he wanted to eliminate all the unnecessary information and just say, this is all you need to know because you're coming here. And so when I look at this, I don't hold it up as an accurate map, but it's a sketch map. It's a way of representing the space so I can get from point A to point B accurately. But it's a sketch that the designer gave me that's referencing a map without being overly slavish to the accuracy. Okay, so now I'm going to move on to some of the mechanics of sketching. I'm just going to flip through, again, some more of the spreads. One of the things, again, getting back to this idea of mapping, because we're in a space where we turn around, create a sketch, build a computer model, I'm always looking for analogies. And so what I'd like to say is that a three-dimensional object, when we're thinking about it orthographically, is really just a compressed three-dimensional shape that's then been brought into a straight-on front or side view. I actually built these models in SolidWorks and just used the compression, the ability to shrink the shape along one axis, and therefore create the visualizations. I found using software like SolidWorks is a great tool to explain how normal sketching happens, because it's a great visualization tool. Similar thing here, when we think about sketching, sometimes a good metaphor is that you're literally tracing, you're leaving a trace of the object. And that works up to a degree, until you have an object like this that leaves the surface of the sheet of paper, in which case you have to project down. Or in the case of that metaphor for trying to trace a spherical shape, it simply isn't going to work. However, if you cut that shape in half, you can now trace it. Sketching, as I like to say to students, is thinking through the object, seeing the object in section, and being able to build it accordingly. Which gets us back to this idea of sketching as physical making. In this case, I use the analogy of building a boat. If I'm sketching something like a boat, I'm sketching in the ribs. And these ribs create contact points that allow me to literally kind of connect the outside shape. But I'm thinking about sketching as literally building a shape rather than this disembodied kind of process that sometimes happens in the computer. Sketching is happening in Cartesian space. So understanding the way in which that gridded space occurs through an X, Y, and Z axis, I think helps anybody when they're sketching to transition from sketch into computer model space. The other thing is that at the end of the day, you have to understand there's a language that occurs with all objects. All objects can be broken down into edges, vertices, and then faces. And that if you're not sketching all of these and thinking about those, you're not actually building it. And I'm going to talk a little bit about how that whole building process works. Again, three-dimensional objects are mapped onto a flat two-dimensional sheet, which, like a box, can unfold. And it creates this interconnected network that connects each one of these views through all of the vertices, edges, and faces, so that it's like an unfolded box that gives you the flat views. Ultimately, though, when you sketch, you don't want to sketch and feel constrained by orthographic methods or horizon lines and vanishing points. You want to sketch as though you're actually building something or cutting something or doing a composite of the two. So again, thinking about objects as having true structure. Again, going back to the boat, if I think of this object as literally having a series of sections, and all I'm doing is connecting those sections together through outline, it's much easier to create a believable three-dimensional shape. Oftentimes students struggle with that because they don't go through the process of actually building the shape. They want to get there without taking the journey, so to speak. I like to use this as an example. It's a Pringle potato chip. Everybody thinks of it as something they're very familiar with, but try to draw it. And what it comes back to is realizing that if you don't understand it in section, you're never going to be able to sketch it three-dimensionally. Once you understand it in section, putting it together in a sketch is really a matter of kind of connecting the dots. And so again, this idea that in sketching you're really building it's central to the process. So here's a quick little scenario of sketching something. Same thing here. This little hand drill. If I understand the front view and the side view, what I'm doing is I'm taking this slow journey and I'm slowly constructing this so that I can start putting information in and just slowly building it. Once I've got that to the point where I can confidently start adding additional sections, I can literally build it part by part to the point where I will have a pretty well realized image, and then obviously adding color brings up the level of fidelity. Okay, so I think there's been a disconnect with sketching in general with its past. So again, I've talked a little bit about the grid, but the grid is really central. It's a central way of understanding space, and it was the way that the Florentine artists understood space, graphing it, overlaying this grid onto space. So if you think about a Florentine interior in the 15th century, or really practically any century, this is what Italians would have grown up with. Very familiar with that kind of space. But it took someone like Filippo Brunelleschi, who's trained as a goldsmith, to come up with a system to actually decode or hack perspective. And what he did was, this is a little model of the baptistry outside of the Duomo in Florence. Brunelleschi made a painting of the baptistry, which is an octagonal form. And this is the painting here. He's looking through the back of it, and he's drilled a hole the size of a lentil that he's looking through the back of the painting. And he's got a mirror so that as he looks through the back of the painting, the mirror reflects back and shows him the image of the painting as he sees it. He's placed all of this in front of the actual baptistry. So by simply pulling this down, the baptistry, which is right here, he can see the baptistry. By raising it, he sees his painting. He pulls it down, pulls it up, pulls it down, and he's able to validate that, in fact, the painting he's made is similar to the actual baptistry. So he created this empirical method for proving the existence of a single point. And you can see it here. The diagonal became a central tool for it. But what you've got is a plan view with a diagonal and a network of points. So all that has to happen is the points have to go out to the diagonal, up and back to the vanishing point, at which point they intersect with a series of projected points on that upper plane. And the same thing here. And what he's doing is he's taking the information, these points, and he's flipping them up to this top view. Once he's got that information, it's just an issue, a matter of connecting the dots. Once the dots are connected, he can go in and he can project upwards and he can begin constructing the space. What was interesting is that Brunelleschi came up with this empirical way of doing perspective. His friend Alberti came in and created the first treatise on perspective, and called Della Pittura. And Alberti's treatise on perspective had absolutely no images. It was entirely text. So basically, Brunelleschi came up with the visual explanation. Alberti came up with the textual version of it, which, if you think about it, is an algorithm, because all it is an instruction set for how to actually create perspective. But simple things like how to accurately establish where the transversals were, all of this was done geometrically, and all of it was explained using text, which is kind of a very interesting thing. So it connects the process of what we now use in computer-aided design to that very ancient method that they first pioneered. This is Jurors Drawing, and what he's using is a window that is gridded. And there's a line that runs through that grid, and he makes a notation at each one of the points on various aspects of the lute. The wire is pulled back, which is on a weight. The window is closed, and he pricks a point on the sheet of vellum that's here. And over time, he has a network of points that are merely connected. Not the fastest way of making a drawing, but what it was doing was creating a sort of precursor, which when you look at Ivan Sutherland's Sketchpad software, which was the first parametric CAD package pioneered at MIT in the 1960s, it's a very similar process. He's selecting a series of points and connecting dots to create geometry. This is a chalice from Palo from 1400s. And this is an updated version in Adobe Illustrator that I created. Adobe Illustrator now does very basic 3D. But you can see that Uccello's chalice and my chalice in Adobe Illustrator are virtually synonymous. So the Italians had really figured out how all that geometry worked. It took computer programmers and a lot of innovators to come up with a software that packaged that into an algorithm and an interface that allowed us to do it digitally. All data at this point now is encoded data. So that's a bitmap of my daughter's eye, and there's my daughter. But when you look at an image like this, back to photography, all this is a series of tiles that have very small amount of information because everything is just a single color with the position and the color encoded into it. So even a photographic image now is just this. It's data. It's encoded data. And that connects us back to drawing as code, and it connects us back to those early pioneers who had figured out how perspective works and then codified it, and in the sense, and in the process, created the code for it. This is software from Microsoft. This is the baptistry. So this is using crowdsourced images of the baptistry. And as a result, you can actually now rotate the object. Although what you're doing is just rotating graphic images of the object. So when we think about what the artist did at this time, back in the 1400s, this is sort of the most recent version of it. So that was the baptistry, and what you're able to do is upload images of the baptistry, and the software stitches all those images together, and as a result you can take your mouse and rotate that baptistry, which was the original object that Brunelleschi had sketched. All right, so we're back to my daughter. This is probably one of the single biggest problems with design sketching as I see it. We're reduced to lines when in fact my daughter has no lines on her face. She's young enough, she's 15, she will soon have lines, but she has no lines. And yet that's what we're expected to create form out of. So I can overlay some contour lines and begin to develop some three-dimensionality, but really at the end of the day I'm relying on this thing called a line, which this could be anything. It could be an apple, it could be a tomato, it could be an orange. If I add a little bit of color, I start to get a little bit closer to it, but really I'm still not that much closer to communicating to you. It still is flat. If I peel the skin off the orange, in other words, if I peel the surface off the orange, now suddenly I've got edges. And so as designers, we're using this to describe everything when in fact there are no lines anywhere. There are no lines in nature. Take something like a torus or an inner tube. It's a completely seamless surface. How do I sketch it? I have to sketch it by constructing it. And so that's a critical requirement for getting designers over that initial issue of how do I sketch something when there are no lines. So I'm going to go quickly through some cognition, and then I think I'm going to have to just stop there. So here's our friend Homer Simpson, kind of a brain inside of a large cavity not being used. One of the things I found that was pretty amazing was of the 180 degrees that we perceive is our cone of vision, in fact, 2 to 3 degrees is all that's ever in focus. So if we take something like a simple photograph, this is Strasbourg, the Strasbourg Cathedral. This is the way a 3-day-old baby would see. And eventually that baby is going to be able to focus on things. But this is how we see. If I want to see her, I'll focus on her, but I won't see anything else. Everything else is out of focus. As I move my vision, she'll go out of focus, and they'll come into focus. And so we direct our vision as we need it, on an as-needed basis. But the assumption is we open our eyes and everything is in focus, when in fact it's not. Probably more interesting is, this is what your brain is actually seeing. It's seeing this amazing array of edges. And what your brain has to do is come in and slowly make sense of it. So not only are we seeing this very narrow slice, our brain has to come in and connect things. It has to bind those edges together into meaningful units. And we're doing this very, very quickly and seamlessly and unconsciously. And so it may seem like I'm overstating something, but let's just zoom in on that one little section and look at all the things. Why would your brain understand that this and this are connected? Okay, there's color, there's texture, but your brain still has to put those things together because the strap is cutting it in half. Her hands, his shirt, his hands, his neck, her hair color, all these things your brain has to parse. But in fact, your brain does it. And it does it very, very well, and it does it very, very quickly. And so when I have a student come to me and they say, I just can't sketch, I say, listen, you're doing it all the time. Your brain is making sense of edges constantly. It's constructing stuff on the fly, and you're just not aware of it. So once you're made aware of it, the hope is that you become more susceptible to the idea that you can learn to draw. So now we white her out. She's looking at the facade of the Strasbourg Cathedral, and we tend to think that we're looking and viewing the world in 3D. According to Colin Ware, we're actually doing the vast majority of our viewing along this axis, side to side, up and down, very little of the z-axis, very little of the depth information. The reason that is that we become very adept at reading depth and understanding depth, and going, moving our heads or moving our bodies to pick up more information just takes more time. So when people say, well, the challenge I have is the flat surface, I say that's what you're actually excellent at doing. So when a student thinks of sketching, sometimes they think of this ability to just put this up like that. I say to them, this is the way I sketch it. I build it, I draw through. One of the key things that the psychologists over the last 50 years have discovered is that the brain does this amazing process of piecing together all those edges that we can't see. It's a normal part of our process. It ought to be a normal part of our sketching process. The brain is also good at what is called invariance, the ability to look at an object from multiple vantage points and still be able to see it as the same object, even though what you're seeing on your optical array might be very different. Urban Biederman, who is a neuroscientist and big AI guy, it was into this idea of explaining how it is we can maintain the names of hundreds of thousands of objects, and came up with this idea of a geon library. 50-some objects, and all we do is we connect those together. And so something like a fire hydrant in geons are just a series of simple primitives that are kind of pieced together. That's no longer an acceptable model for how we think, but it's still a very good model for how we can sketch. Because in fact, piecing things together is a perfectly good way, as I showed earlier. Okay, so I think I'm just about out of time. What I'm going to do is just wrap up here. Yeah, it's 5 o'clock. So one of the late chapters just compares building objects in computer-aided design programs, in this case SolidWorks, with the sketching process, making the direct comparison to how you would build something in the computer and its analog in sketching. That they're very, very similar processes. It's just a matter of kind of twisting your brain to realize that when I sketch this, I'm basically doing sort of a revolve, I'm doing an extrusion, I'm doing this very similar kind of process, just in sometimes a different order, or doing different kinds of shortcuts to get there. So these are sort of like case studies within the book describing the process of actually building three-dimensional form. So Ed, I'm right at 5 o'clock now, so I don't know. There's a section on scenarios, but that's another 10 minutes. So if we end here, that's fine. We could have a Q&A or.
I think we have the room for like 5:30, but I think generally speaking, around this time, people want to begin to ask questions.
Sure, sure.
Maybe we can get that track.
You know, and maybe I'll then jump to another part of the presentation if it comes up. So I'll be happy to take any questions.